Hi, everyone. Well, we've been talking about nanostructures, and today we're going to focus on applications. In particular, applications of quantum wells, these two-dimensional nanostructures that have a confinement in one dimension, thin films. What we're going to find out is that quantum wells can be used to make better light emitters and faster transistors, and also to make some interesting quantum devices that only operate on the basis of quantum principles. Here, let's take a look at the outline. All right. So as I said, we'll show that quantum wells can be used to make better light emitters and faster transistors using a trick called modulation doping. We'll talk about in a minute. And then finally, we'll talk about some interesting quantum devices, something called a resonant tunneling diode, and a device called a quantum cascade laser. All right? Well, here, let's go ahead and get started. All right, well, to begin with, quantum wells can be used to make better light emitters, that is, more efficient light emitting diodes. And we can illustrate this process if we look at these diagrams. And the first, of course, shows the band energy as a function of position as we go through our thin film, okay? In the quantum well, we only have confined subbands, and I'll just sketch in the minimum energy in the lowest electron subband and the maximum energy in the highest hole subband. If this is set in a p-n junction, then when we forward bias the junction, electrons will collect in the quantum well because that's a position of lower energy for them. And likewise, holes will collect in the hole subbands of the quantum well. And so we'll have a high concentration of electrons and holes in the quantum well. We can also view the process in energy space. In this diagram, we have electrons in the lowest electron subband and holes in the highest hole subband. And then these can recombine. And when they recombine, energy will be emitted. There we go. Okay, that's the process we want to look at. So of course, one of the issues is that this kind of recombination always competes with dark recombination. That is, processes where the electron loses energy but doesn't give off a photon because the energy ends up being dissipated as heat. Okay, you have to work hard to make light emission the most efficient process. And to do that, you'd like to maximize the radiative recombination rate. Now, this recombination rate depends on a constant called the rate constant times the concentration of electrons times the concentration of holes, because we have to have both an electron and a hole get together in order to have light emission. So it's clear here that because of these concentrations, that because confinement in a quantum well boosts the electron and hole concentrations, it'll increase the recombination rate of those electrons. So that's the main thing. That's the most important mechanism. There's another one as well, though, which we should take a look at. The recombination rate constant, R, turns out to be proportional to the density of states for electrons times the density of states for holes. And we're really interested in the density of states at the minimum energy of the electron subband and the maximum point in the whole subband. These are the band edges, if you will, for our quantum well structure. That's the lowest energy position for electrons, highest energy positions of holes. That's where they'll tend to accumulate, and that's where we're looking for recombinations from. Okay? Okay. And it turns out that the density of states in these points is much higher in quantum wells. Than compared to bulk. And this is kind of interesting. So I thought we'd take a look at it. Here's the idea. Remember, we said that the electrons in quantum wells are a free electron gas, just like the electrons in the conduction band of an ordinary semiconductor are, okay? And if we had electrons that could move around in a quantum wire, they'd also be a free electron gas. Only while they're a three-dimensional gas in the bulk material, and they're a two-dimensional gas in the quantum well, and a one-dimensional gas in the quantum wire. And it turns out this affects the density of states. And we actually have done a lot of work already that will help us figure this out. Because we've already talked about free electron gases. Okay, so let's spend a moment now to work out the density of states in nanostructures, or at least to find out how these scale with energy so that we can compare them. Okay, so first of all, what the density of states is it tells us how many orbitals there are in each band of energy. Okay, or really it's just the rate of change of the number of orbitals or a number of electron states with respect to energy. Okay, and we found how the Fermi energy depends on the number of electrons or number of holes previously. And we've already done this for 3D and 2D free electron gases. And we may have done 1D as an example, or we may end up doing this as a problem, the easiest case. But in any event, let me summarize what we found. So here, I'll make a little table for 3D, 2D, and the 1D cases. And in the 3D case, the Fermi energy is proportional to, oh, here, I'm just going to finish making my table. I'm sorry. Oh, and I think I'll just move all of this down a little bit. There we are. Okay. So we found that in a three-dimensional electron gas, that the Fermi energy was proportional to n to the power 2/3. You can go back and look at this if you like, but that's what we found. You also looked at the two-dimensional case as an example, but we'll come to that in a moment. So that's how the Fermi energy depends on the electron concentration. We can invert that to find how the density of how the number of orbitals depends on the energy. And you can see it just goes like energy to the power 3/2, just inverting that formula. And then the density of states is just the derivative of n with respect to E. And so this is proportional to energy to the 1/2. Okay? In 2 dimensions, we found in a homework problem that the Fermi energy was just proportional to the number of electrons. And that means that the number of orbitals is just proportional to energy. And this turns out to mean that the density of states is just a constant. Okay, something you showed in the homework as well. And finally, in the one-dimensional case, it's easy to show that the energy goes like n squared, so that the number of orbitals goes like e to the 1/2. And so the density of states then would go like e to the -1/2. Okay? These are sort of nice results. Let's put a box around them. Okay? I'm going to try that once more. Oh my gosh. Very particular about my boxes. There we are. Okay. Here, let's see what these formula mean. All right? 1 second. Okay, what these mean then is that in a three-dimensional system, the density of states varies with energy like this. At the conduction band edge, it increases from 0, but it increases like e to the 1/2. Okay? And that means that very close to the conduction band edge, it's actually very small. And that's kind of a problem for our light emitters, because it means that the rate constant for recombination will be relatively small. On the other hand, in a 2D system, the density of states starts from 0 and it jumps up to a large constant value. Okay, here we are. So that at the minimum energy, the density of states is already quite appreciable. So that's a big improvement. Thereafter, it remains constant until we reach the energy where the next confined subband can participate, where electrons in the next confined subband can recombine. And at that point, the density of states jumps up to a new constant value, and this continues to happen. But the most important thing is down here at the minimum energy for transitions. Finally, for a wire, it's interesting to see that because the density of states goes like e to the -1/2, it actually diverges at the band edge, at the minimum energy. So it's very high here, and then drops off like 1 over e to the 1/2. And then when we get the next confined subband, we get another spike and another. Okay? Oh, and finally, what about the case of quantum dots? For a quantum dot, there are only discrete states at discrete energies, like the states in an atom. And so, of course, the density of states just has a single spike at that point, at the point of the next energy state and the next energy state. So these look like delta functions, if you will. Anyway, we can compare them all. But the worst one is the three-dimensional case. Here, hang on. So what does this mean for light-emitting diodes? So we have these two important points. The recombination rate increases because the density of states, the transition energy is much larger in quantum wells, and it also increases because the concentration of electrons in holes is much higher in the quantum well. And that produces results like this. So this is light emission from gallium nitride measured in my lab. These aren't LEDs. Instead, the material was being excited with ultraviolet light, and then we get light emission in these two different cases. So the first you can see is a gallium indium nitride quantum well grown in gallium nitride. And we see a high intensity of luminescence, a lot of light is emitted, okay, at particular energy. The second case is some bulk gallium nitride with no quantum well. Now, you can see that the emission is at a higher energy here because the band gap of gallium nitride is higher than of the quantum well material. But the other thing you can see is that this is much less efficient. This peak is much smaller than that one. And the number, and this has already been multiplied by a factor of 100. If we put these at their true relative scales, you wouldn't even see the deviation of you wouldn't even be able to see the signal from the bulk gallium nitride. So the quantum well emission is about 1,000 times more efficient than the efficient from the bulk material. And as we mentioned before, for this reason, essentially all light emitting diodes are made from quantum well systems. Okay, so there's our first application of nanostructures, and it's a very important one. All light emitting diodes are actually nanostructures. They're actually quantum wells. All right, let's stop here.